Prithviraj will be live in 2 seconds. I'm sending you the link.
Yeah, I can see. I called Saikia sir once. Then, Jamir sir,
Yeah,
should I give Saikia sir a call once just to ask
yeah,
him?
that's what I was saying. So just give a call.
Yeah, yeah, I'll call him. I'll call him.
Yeah, sure.
He's joining. He was just trying to find the link in the mail, so I sent it to him now.
Hi, Sykes.
Hi, Jamir. 1 second, my volume is very low. 1 second.
Yeah,
Yeah, now it's okay, I think. Yeah. Hi, how are you?
I'm doing.
Okay, one
How are you
second.
doing?
I'm all right, actually. Thank you very much. Yeah, 1 second. Yeah, I'll just try 1 second. I'll
Yeah, you can
close
share your
these.
screen.
1 second. I'll just close other windows. Yeah, 1 second. Don't think I need this also. Okay. Should I try to share? I'll just try to share 1 minute.
Yeah, you can share.
Host, okay, you have to make me a co-host, otherwise I can't share.
Yeah. Pranjal, so
Pranjal, can
can
you
you?
make? Yeah, can you make Saikia sir the
Yeah,
co-host?
done.
Done?
Okay.
Okay, 1 second, let me see. Black holes in a universe. Okay, share.
Yeah, we can see.
Yeah? Okay.
Yeah, we can see your screen.
Okay.
So maybe you can put on a presentation mode.
I can do the slideshow, no?
Yeah, slideshow.
Okay.
Yes.
Slideshow from beginning. Okay. That's fine?
Yeah, this is perfectly fine.
Okay, wonderful.
We can see.
Okay.
Rudraj, you can allow people.
There are quite a few people waiting in the. You can
Yeah.
probably disable the waiting room. 19
Yes.
people entered the waiting room.
Yes, we'll just admit all them.
Okay, we have a few minutes left. So I'll just get myself something to have a drink. Okay.
Sure. Pranjal or Rudraj, can you disable the waiting room? Either of you, so that people will directly join.
Pranjal, I think you may have to do it since you're. Okay, no, I disabled it.
Done it.
Okay, good. And also make sure, like, accidentally or by mistake, someone, if they unmute themselves and they talk, so you have to take care. Okay,
Yes.
you have to moderate it. Yeah. Yeah, we'll wait for a couple of minutes, then we'll
Yeah,
start.
please do. Yeah, no problems. You wait as long as you
Okay.
want to. Yeah.
Yeah, thank you.
Jamil, can they unmute if in between if they want to ask a question?
I
Or
guess yes.
yeah, okay. So if I ask them a
Or
question,
either they can raise hand. If they are not able to unmute by themselves, they can raise hand and we can ask them to unmute.
okay, but they can also unmute, no?
Yes,
Okay, okay, thank you. So I can ask them questions also.
sure. Yeah, maybe we can start, Pranjal.
Yeah, this Rudra Mandal has said no sound, but I think the problem is with his system
We haven't
probably.
started yet.
Yes,
Yeah.
No,
I guess
I
so.
I think the issue was that I think he thought the talk started, but we haven't started yet.
Okay, okay,
Maybe
okay, okay.
Yeah, I guess now.
should we start?
Yeah, please go ahead.
Uh, Hello there, everyone. Thank you for joining us today. I am Ruturaj Kulkarni, a third year physics major at IISER Kolkata. I'm an office bearer of Singularity, which is the astronomy club of IISER Kolkata, and more importantly, a member of the ISAC core committee. Before we begin, I'd like to take a moment to briefly introduce ISAC, since this is our very first event. ISAC stands for the Indian Synergy of Astronomy and Astrophysics Clubs, and it is a student-led nationwide network of astronomy clubs. The idea for ISAC started earlier this year, and more so around June, when it was first proposed by our club. And what began as just a conversation about how isolated most clubs feel, it slowly grew into something real. And by August, with help from clubs across the country, ISAC was officially founded. Our aim is simple. We wanted to create a space where astronomy and astrophysics clubs across India are actually connected and actively working together, not just in name but in practice. We currently have 50 plus clubs from institutes across the country, and the goal is to build a community where we can share resources, collaborate on events like workshops, learn from each other, and mostly make opportunities more accessible, especially for students who may not have access to equipment, guidance, or exposure. And we want this to be something that stays active, grows over time, and benefits students long after all of us graduate. I'm extremely happy with such strong participation here today for our very first event. It's a small start, but it is the first of many more to come. And with that, it's my absolute honor to introduce our speaker for today, Professor DJ Saikia. Professor Saikia is one of India's most respected radio astronomers. with a career spanning more than 4 decades of research and teaching in field. His work has contributed significantly to our understanding of extragalactic radio sources, active galactic nuclei, and their interstellar medium. He began his research at the Radio Astronomy Group at TIFR and has since held scientific and academic positions at several leading institutions, including NCRA TIFR and IUCA. He is currently at the University of Bielefeld in Germany, where he is associated with the astroparticle physics and cosmology. Professor Saikia has also been deeply involved in astronomy education and outreach throughout his career, and we are very fortunate to have him with us for the inaugural event of ISA. His talk today is titled Black Holes in Our Universe, where he will discuss the observational evidence for black holes and the role they play in shaping some of the most energetic phenomena we see in the cosmos. Please join me in welcoming Professor Saikia.
Okay, so I can start now?
Yes, sir, please go ahead.
Okay. First, let me congratulate Rituraj and all your friends and Jamir, who's also been behind it in the formation of this consortium of astronomy clubs across higher education institutions in the country. I think it's a wonderful idea to get students from across institutions together, help each other out, and create resources as well as a forum for interaction among the community over here. And congratulations to all of you who have been part of this endeavor. And I hope, and I'm sure, and I hope it'll continue to grow and be useful to the students across the country. And also, let me thank you very much for a kind and generous introduction, and also the privilege of speaking on the first event of this newly formed initiative. And thank you very much for that. So today we will discuss about black holes in our universe. And what we will do is that we will approach it from an observational perspective. Even hardcore theory is actually driven by observations, as you will see, not only today but in future lectures as well. And due to the limitations of time, it will not be possible to cover all aspects of it. But I'll try to give you a broad overview of where we are today. And since I've assumed that all of you would be from a wide background, some of it would be introductory, which I will go through more rapidly. Some of it a little bit more advanced, and which I will try to present without getting into the nitty-gritty details. And and I hope that some of it, at least a lot of it, will be new to many of you. And thank you very much for all of you attending today, because on a Sunday afternoon, nearly 100 of you to be there is wonderful, actually. Okay. Before I start off with the discussions, I would also like to state that you're free to ask me questions at any time during the presentation or discussion, and I will also periodically ask you questions so that it is a bit more interactive, and hopefully we'll all get something out of it. So let me start off now. So what you can see over here is the iconic image of M87. The first black hole to be actually imaged anywhere in the universe. Okay, and the Event Horizon Telescope, which made this image, actually had two targets. One was M87, which is an elliptical galaxy we'll see in a short while, and also in the center of our own galaxy, the black hole in the center of our galaxy, the Milky Way. And these have been made with the Event Horizon Telescope at millimeter wavelengths, and with a resolution of about 20 microarcseconds or so. And you can see the scale which is given over here. And what you see over here are images which are made on different days. And M87 image was published earlier. That was just a wee bit little challenging than mapping the black hole in the center of our own galaxy. And that is because you make observations over a certain duration of time. And in the case of the M87 black hole, because the black hole is more massive, that the material is stable for a longer period of time for the observations to be made. Whereas in the case of the black hole in our own galaxy, which is less massive, the Schwarzschild radius, which we'll meet again in a short while, is much smaller. Things change much more rapidly. So it's a bit more of a challenge compared to M87 to map it, but the beautiful images of the Milky Way black hole also, which has been imaged. And what I should say over here is that whatever we have known so far about the black hole in M87 is consistent with Einstein's predictions of the general theory of relativity. And there are alternate theories of gravity as well. And in the future, when we are able to image this black hole with even higher resolution than what we have been able to do, we may be able to actually try and either verify or reject other theories of gravity. But today, Einstein's theory of general relativity has really stood its ground in a wide variety of tests, including images of the black hole, which you see over here. And so let me tell you a little bit about M87 before we go ahead. M87 is an elliptical galaxy in the center of the Virgo cluster of galaxies, and stands for Messier. Messier was an astronomer French astronomer who wanted to study comets, and he made a catalog of diffuse objects in the sky so as to not to confuse his observations with other diffuse objects. And these objects goes by the name of Messier, a set of objects which are very popular among amateur astronomers because they're bright, they're diffuse, and they're relatively nearby. And it consists of all kinds of objects. It consists of galaxies, it consists of star clusters, it consists of planetary nebulae, which are the remnants of evolution of low mass stars, or the remnants of massive stars which explode, supernova remnants. But this particular one is an elliptical galaxy, which you can see over here. It's at a distance of 16.8 megaparsec. 1 parsec is 3.26 light years, so it's slightly over 50 million light years or so. And something interesting was noticed about this galaxy way back in 1918 itself, more than 100 years ago, when Herbert Curtis noticed that unlike other galaxies that they had observed, it had a faint wisp of light. He said a curious straight ray lies in a gap in a nebulosity, apparently connected with a nucleus by a thin line of matter. The ray is brightest at its inner end, which is 11 arcsecond from the nucleus. That was published in the publications of the Lick Observatory, as I mentioned, over 100 years ago, 1908. This is one of the very well-studied objects in the universe. And at that time, nothing was known about jets. Nothing was really known about black holes as well. They were not, supermassive black holes was not really thought about in terms of being at the centers of galaxies. And this was taken up many years ago by Bardeen-Minkowski, who observed it and said that several strong condensations are in the outer parts of the jet, which extends about 20 arcsecond from the nucleus and has an average width of 2 arcsecond. They were among the first ones to use the word jet, and a jet is an outflow of collimated relativistic plasma from the nucleus of a galaxy, and we believe that it has all to do with the supermassive black hole or a massive black hole which resides over there. And they also detected a line which was blue shifted by about minus 300 kilometers per second or so, and they speculated that this must be due to ejection from the nucleus. And today we know that this jet is actually moving relativistically. What you see over here is actually an image made at infrared wavelengths by the Spitzer telescope. And what you see in the back, this is the narrow collimated features which Curtis talked about, which we will show you in a little more detail in a short while. But what you see in the infrared is also emission on the opposite side over here, a blob of, a region of emission like an inverted C shape over here. We'll come to that in a little while, okay? Now, these are images at different wavelengths. And what you see over here is a radio image at different wavelengths, okay? And this is with the VLA, the Very Large Array Telescope in New Mexico in the United States. And what you see is a nucleus over here, and a one-sided radio jet and diffuse plasma over here. And there is also diffuse emission, and all is emission at radio wavelengths. Here there is no color. The color is actually false color because radio wavelengths is not something which we perceive with our eyes. And it is just to illustrate the regions of emission and the relative brightness. Then if you look at just this little jet over here, this is what an optical image shows you. There is a strong condensation over here. There is a very prominent, not very close to it, called HST1. And if you look at this with higher and higher resolution, you begin to see the jets also coming out. And just what we saw a little while ago was the image made with the Event Horizon Telescope. And from the size of the ring, which is the Schwarzschild radius, the event horizon, we'll talk about that a little bit more. One can go and also estimate the mass of the black hole. And this is one of the more accurate masses, which is about 6.5 billion times the mass of the sun, which is a few times 10 to the power of 33 grams. And here I've also written down the Schwarzschild radius and the diameter of the ring. Okay, so let me just ask you a question right now. These observations by the Event Horizon Telescope has been made at millimeter wavelengths. Okay, can one of you just unmute yourself and tell me why you think it is being made at millimeter wavelengths? It's at 230 gigahertz roughly, which is about 1.3 millimeters or so. Anyone? Not Jamir, okay?
Is it
Any
is
one
it
of you.
because of the redshift that happens because of such long distances?
No, not because of the redshift, because the black hole, actually, compared to the distances that we're talking about today, M87 is really close by. It's just about 50 million light years away. So, and it has a very, very moderate redshift. Okay, but anyway, I'm very happy in this for at least, I mean, you're thinking, and that is important. Okay, and that is important.
Sorry, thank you.
Okay, anybody else? It doesn't matter whether you're right or wrong. I just want you to be thinking. And thank you very much, Andrews, for participating. Anybody else?
Is it to peer through the gas cloud above and like around the black hole?
That's also an interesting, a very interesting thought. Okay, Zaid, interesting thought, because what happens is, I mean, you could have observed at 5 gigahertz as well, but you'll still trace through the clouds. But what you're saying is very important in the sense that at radio frequencies, the absorption by the interstellar medium of the host galaxy is negligible, is very small. And so at long wavelengths, like radio waves, you can peer right into the central region of a galaxy or very dusty regions. For example, the center of our own galaxy, there's so much of obscuration by the interstellar medium of our galaxy that you cannot see it in the optical, but at radio you can go see it. So in the sense that radio wavelengths is important to be able to see through the gas and dust, and so that is an interesting thought, and that is partially correct, but it still doesn't answer the question as to why we are observing at millimeter wavelengths.
Thank you, sir.
Does it have to do anything with Hawking radiation?
Not with Hawking radiation, no. Okay. It's something very basic which all of you would know, which is the resolution. Okay. For example, what you see over here, the images on the left, you see, as you go to higher and higher resolution, you can see smaller and smaller scale structures. For example, when I look at the bottom radio image where my cursor is, you do not see the large scale diffuse emission over here. Okay, because the way the radio images get made is that you may or may not, some of you may have been introduced concepts of Fourier transforms, but basically what the radio interferometers or the radio telescope sample are the Fourier components of the brightness distribution. So when you have antennas which are very well separated, you will see the small scale structure. And when the antennas are close by, you'll see the large scale structure. So you try to combine small and large scale structure, but the objective of the Event Horizon Telescope is really to image the black hole, right? It's to image the vicinity of the black hole. So you really need the highest resolutions, okay? Now, what does resolution depend upon? The Rayleigh criterion, right? Rayleigh criterion is what? Is roughly, without worrying too much about the constant factor, lambda upon d, right? Lambda upon d. So what you want to do is you want to have enough sensitivity as well as resolution. And to get higher resolution, the smaller the lambda you have, the higher the resolution you will get. All right. And that is the reason why they have chosen millimeter region so that you could get the highest possible resolution. And also, as you will see in a short while, the Event Horizon Telescope is literally Earth-sized in terms of the baselines. If you want to increase the resolution further, in order to, for example, say, distinguish between different theories of gravity, you need to go to even higher resolutions. So what should you do in that case? One is, of course, increase the frequency. Millimeter wave technology is, has developed tremendously over the years. And so you want to go to higher frequency so that your lambda is even smaller, and you want to increase the baseline. Today, the Event Horizon Telescope has baselines from the South Pole till Greenland. So you can't go much beyond that. So to increase the baseline, you'd have to put a telescope in space. So these are aspects also which are being talked about. But today what we have is more telescopes added to the Event Horizon Telescope, and some at shorter baselines as well. And shorter baselines have been able to see wisps of connection between the black hole and this, jet structure right in the vicinity of the black hole, and that gives us ways to understand how jets form and jets get collimated. So remember that resolution is the important criterion, and we'll meet that again in a short while. Okay. Let me see, how am I doing? Okay, 11. No, I'm going a bit slow. Okay. Right. Okay, let me go a bit more rapidly. Okay. Now, what did I do? Okay. Our galaxy, also the Milky Way, has a black hole, as I said, and we will talk about that a little bit more later. And one of the very interesting things which was found from in the vicinity of in our galaxy, is that our galaxy doesn't have the kind of jets which I talked about in MET7. But what was discovered initially with the Fermi telescope at gamma ray wavelengths, and more recently with the eROSITA telescope at X-ray wavelengths, is that the huge bubbles of high energy relativistic plasma which are emitted. For example, this particular sketch just shows you where we are located, the solar system. This is about 8 kiloparsec. 1 parsec is 3.26 light years. So it's about 26, 27, 28,000 light years kind of thing. And you can see on a much larger scale, almost the whole sky is, a major part of the sky. We don't see it because we don't see X-rays or gamma rays, but these are very, the total energy content is very large, about 10 to the power 50 something ergs, but the brightness, surface brightness is very low. All right, and there are various sort of papers arguing what the reason might be. As many speculate and also suggest that perhaps the black hole has a very significant role to play in the generation of this plasma, although we don't see the kind of jets which we saw in MET7. And I'll just show you the image of our galaxy as well. And you can see that the Schwarzschild radius, which I'll talk about a little while later, is much smaller. You can see that given the relative scale of the two images over here in physical dimensions, this is the sun's diameter, and you can see that this is the size of the Schwarzschild of the ring of material, a ring of photons, a ring of light coming from around the black hole in the center of our own galaxy. And in MET7, it is much larger. But because this is much nearer, the angular size is sort of, you can see that the two rings are not hugely different in terms of angular dimensions. Here, the physical size is larger, but it is further away. So the angular size is, comparable to an object which is much smaller, but much closer. And because of the resolution which is possible with the Event Horizon Telescope, that when they started off, these were the two main targets of trying to image the vicinity of the black hole. Okay, and they have actually been observing other AGN as well, but because they're more distant, it's difficult to get the kind of images which you see in the case of M87 or the center on galaxy. This is another nearby radio galaxy, Centaurus A. It is one of the first initial radio galaxies to be identified because it was relatively close by. It is only about 500 kiloparsecs away. Okay, and it has a supermassive black hole, smaller than that of M87, but more massive than that of the Milky Way. And because of its close by, the angular dimensions are large, but physically it's about 500 kiloparsecs away. 1 parsec, remember, is 3.26 light years. And you can see over here that they've been able to not quite image the jet, but image the black hole, but you can see images of the jets over here. And you can see that there is sheets of plasma which surround which are visible. And these have had important uh, input in terms of understanding jet physics and how jets develop and grow, and have been very valuable inputs in our understanding of relativistic jets. A little bit about the Event Horizon Telescope. You can, as I mentioned, it extends from the South Pole Telescope to the Greenland Telescope. There's a NOAA, the Iram Telescope over here, JCMT, the James Clerk Maxwell Telescope in the higher, then the Atacama Millimeter Array, then the Atacama sort of Pathfinder experiment. So you can see that they're largely, the longest baseline is from Greenland to South Pole, but more telescopes are being added and to sort of to get some of the nearby baselines as well, and to give us the kind of images which you see over here, and also probe structures at different levels. Okay, just to give you an idea of the resolution, lambda by d, which we mentioned a little while earlier, diameter. If you had a 5 rupees coin at a distance of about 100 meters, it would be about 47 arc seconds. The resolution of the eye is roughly about an arc minute. And then if you to put it at 1,000 kilometers, it will be at a milliarc second level. And the kind of resolutions which the Event Horizon Telescope has achieved is about 20 micro arc seconds, and it is equivalent to about an orange on the moon. Okay. And today, VLME observations have been routinely done. There are different arrays. For example, this is a very long baseline array in the United States. There's a European VLBI network. The GMRT has also participated in a couple of experiments, but it's not a routine thing which is being done with the GMRT. But some of these, arrays, they routinely do very long baseline interferometry to try and look at the universe with high resolutions. So M87 and Centaurus A we talked about are examples of active galactic nuclei, and the AGN luminosity, the active galactic nuclei are referred to as AGN. The luminosities are huge, 10 to the power of 43 to 47 ergs per second per nucleus, per second from the nucleus. To just compare it with the sun, for example, it's about 10 to the power of 33, so it's about 10 to the power of 10 suns, right from a point-like object in the center of the active galaxy, center of the active galaxy, and it is believed that this energy source is due to accretion onto a supermassive black hole. And there are various arguments for it, and these objects also have very prominent emission lines with large velocities. Okay, and the masses of the black holes are even goes to about 10 to the power of 10, but about a million to 10 to the power of 10 solar masses or so. Our own galaxy is a few times 10 to the power of 6, whereas the most massive galaxies are 10 to the black holes are about 10 to the power of 10. Okay. Now, I mentioned about usually prominent emission lines with velocities of thousands of kilometers per second. Okay, these are very wide lines actually. Can you, from your knowledge of physics, can you tell me what might be responsible for such broad lines in the nucleus of active galaxies where we have large supermassive black holes? Any of you can unmute. Go ahead, Indra.
I think I might be wrong again, but is it because the space-time is too curved near supermassive black holes?
No, absolutely right. I mean, it's just the effect of the very good, interesting. It's just the effect of the supermassive black hole. Because if you look at planetary motions, for example, you'll find that the nearby planets, just by applications of Kepler's laws, are moving much faster than objects which are further away. So exactly, objects, line emitting clouds which are close to these black holes have large velocities, and this is entirely due to Keplerian sort of motion. One can put general relativistic corrections, etc. But basically, it is the effect of the black hole. Excellent emphasis. Okay. All right. Now, let me see how we are doing. So, Rituraj, we have 2 hours, so I thought I would speak for about 1 hour, 15 minutes and leave more time for discussions. Is that okay?
Yes, sir, it's fine.
Okay. Anyway, if it's too simple, you let me know. I mean, I'm also getting a sense because when I ask questions, you'll are answering, and I'll keep doing that. Okay. So black holes occur over a wide mass range. Okay. Stellar mass black holes. Uh, I mean, typically it's less than 100 solar masses. Okay. And intermediate mass black holes are what we refer to as 100 to about 1 million solar masses. Okay, some people would put it as 10 to the power of 5, but one's not going to fight about the numbers. But just to understand the ballpark that we are talking about and where they might occur. And then we have the supermassive black holes, which we just talked about, in the centers of active galactic nuclei. And there is also primordial black holes, which have been theoretically sort of predicted. But since today's is largely focusing on observations and the observational aspect of black holes, we will not delve into primordial black holes today. Okay. Now let's we'll look at each one of them in turn, how they're discovered and some aspects of it. And we'll also in the end try and talk about what are the outstanding questions which we still have to address. Okay. Now, just to give you a brief historical outline I go through it rather rapidly. I mean, the fact that light may not be able to escape from a very massive object was thought about a long time ago, right from the time of Newton. And Newton actually thought about of a cannonball experiment, which actually got published after he passed away. And he said that if you stand on top of a sort of tower over here and throw a cannonball at different velocities, how is it going to move? And this is something which you're all familiar with. But from that we get to value, get the concept of an escape velocity. And we want to, for a black hole, it is, from where light itself cannot escape, not the material particles cannot escape, but light itself cannot escape. And that concept was there for quite a long time. And in fact, people talked about, even an object or a stellar object from which light may not be able to escape. One of the early ones was John Mitchell, who gave a talk at the Royal Society in 1783. Light would not leave a massive star if gravitation is sufficiently large, and speculated that should such an object really exist in nature, its light could never reach us. Laplace also described massive stars from which light may not be able to escape. So you can see these thoughts were there from very early on. And in terms of Newton's gravitation, we talk about material particles and we talk about light cannot escaping. And this is based on, balancing gravity with centrifugal forces but cause of gravity, gravitation itself is something which puzzled Newton as well, because it acts instantaneously. And he had written to one of his friends, Richard Bentley, that the cause of gravity is what I do not pretend to know. He gave a mathematical formulation. He made a big leap to formulate a universal, law of theory of gravitation law. But it was difficult to understand what was causing it. And Albert Einstein, it was Einstein's theory of relativity, which sort of tried to address that, where gravity is a manifestation of the curvature of space determined by matter. So if curvature is weak, then solutions similar to Newtonian formulation, but with strong gravity, it deviates very much from it. And when matter is curved, when space is curved, we need a geometry to deal with curved space. And that was something which Einstein learned and while formulating his theory of gravity. And historically in college we'd have learned about Euclid's geometry, but as you grow, some of you may have already learned it, some of you will learn slowly that we have to deal with curved space-time and surface of a sphere or hyperbolic spaces where the same Euclidean theories will not hold. But for our purpose today, just to quote John Wheeler, that in terms of movement of light or movement of particles, that space-time tells matter how to move, and matter tells space-time how to curve. So geometry or curvature is described by a metric. And again, we will not delve in too much into details of the metric. But a metric can describe both a curved space-time as well as a flat space-time. Okay. And it was the solutions of these Einstein's equations that led to the formulation of a black hole from which light may not be able to escape. One of the early solutions was by Schwarzschild himself. It was by Schwarzschild, and that is quite an interesting story as well, because he was a very accomplished physicist and a mathematician, but he joined the war effort. And while he was a German army lieutenant and in the front lines, he received his bulky packet. And it was a long and detailed, was Einstein's work on gravitation. And he actually worked on it. He worked on it and tried to find solutions from it. And he actually found a solution which describes the black hole, describes the Schwarzschild radius, as we call it today, from within which light will not be able to escape. He didn't coin the word black hole. That was done much later by John Wheeler during a lecture in 1967, and that continued to stay. Okay, so basically, if you look at the structure of a black hole, we will look at it very briefly over here. The Schwarzschild radius actually describes any body with mass, okay? Any body with mass. This is a constant, the gravitational constant, and this is the velocity of light. But what you can see over here is that if you calculate the Schwarzschild radius for the sun or for the earth or for the moon, that the size of the object is much larger than the size of the Schwarzschild radius. So we're not really looking at the effects that we would normally be looking in a black hole. So supermassive black hole is only about 1.9 into 10 to the power 13 meters. That is the size of the Schwarzschild. That is the size of the Schwarzschild radius, and the black hole is really a singularity. Okay, and it is characterized by mass, angular momentum, and charge. So the solution Schwarzschild found was for that of a stationary black hole, a non-rotating black hole, and that was extended to a rotating black hole by Roy Kerr, who still lives in New Zealand. He's about 90-something, 90 plus years old right now. And to describe the brief sort of features of a black hole, I'll just show you over here. One is a singularity. The point at which all the matter and energy that fall into a black hole ends up here. Right outside is the accretion disk over here. That is when matter gets accreted onto a black hole. It has a certain angular momentum. Perpendicular to the axis, it collapses, but along the axis it collapses, but perpendicular to it, it forms a disk. Okay. Now we have the event horizon or the Schwarzschild radius over here, and then we have the photon sphere. Photon sphere is right outside the event horizon, where supermassive and stellar mass black holes' gravities are strong enough that photons which normally travel on straight paths get stuck in circular orbits over here. Okay, get stuck in circular. They outline the shape of a black hole, and this is what we are trying to image as well. And part of the accretion disk will also be picked up. They outline the shape of a black hole. Synthesis the telescope big enough. This picture is from earlier than when they were imaged, to detect this ring around the Milky Way supermassive black hole and see the shadow over here. And the last stable circular orbit is what is denoted by the edge of the accretion disk over here. And relativistic jets are suggested to go along an axis which is perpendicular to the accretion disk. The formation of the jets is a very interesting field by itself, but today we will not touch upon that because of the shortage of time. We will just look at the evidences for black holes in our universe. Some other time, maybe perhaps we can talk a little bit more about jets. Now, one thing which I should mention over here, that the Schwarzschild solution was for a black hole which was stationary, in the sense that it was a non-rotating black hole. But the black hole can also be rotating and has angular momentum associated with it. And the angular momentum is related to the mass of the black hole again, and also characterized by a spin parameter. It's written as, I didn't write it over here, I should have, J is equal to A, G, mass of the black hole squared, divided by C, and A is the spin parameter. So J is proportional to A. If A is equal to 0, it's a stationary black hole. If A is equal to 1, it's a maximally rotating black hole. Now, when you look at the Schwarzschild radius of a black hole, for a stationary black hole for the Schwarzschild solution we just mentioned, it's 2 gm by c squared. If I actually take a rotating black hole, you have to add a term into 1 plus square root of 1 minus a squared. So if a is equal to 1, then 1 minus 1 is 0. So you get the Schwarzschild black hole, which is gm upon c squared. Okay, gm upon c squared. So the Schwarzschild radius is smaller. So what happens is that depending on how the material is moving, in a rotating black hole, you can extract energy out of it more easily because you can actually approach closer. But it also depends a little bit detail on whether the motion of the material is prograde or retrograde. And prograde is the one where you can, get very high efficiencies as well from a rotating black hole. I think the highest estimate or ideal estimate is about over 40% or so, which is much, much more efficient than that of nuclear reactions which power our sun. Okay. So I just want you to remember two things. That one is that a black hole is characterized by the Schwarzschild radius, which is the event horizon, and within which light will not be able to escape. There's a photon sphere where light actually traces, is trapped within its orbit, in circular orbits, because matter is, space is really curved over there, as per Einstein's theory of gravity, and in fact, it's so curved that you can actually maybe able to see light from the back as well, when you look at a black hole, the light which is coming towards you, and then when it forms an accretion disk, you have an innermost circular orbit, and extraction of energy is via the rotational energy or energy from the black hole. And the closer you can go, the more energy you'll be able to extract out of the black hole. Now, looking at the black holes of different masses. Okay, there's a question over here. Okay, Sertunio, let me see what it is. Does a rotating black hole dissipate energy at a faster rate and have a shorter lifetime? Okay, that's a very good question. Okay, what also happens is that black holes can also grow in mass when it is accreting matter from it. Okay, and so one will have to look at the detailed physics of the development of a black hole, because today what we see is that is one of the key questions, is trying to understand actually how these massive black holes have developed. And to extract energy, you need accretion of matter onto the black hole to get energy out of it. But the accretion can also lead to the growth of black holes, or merging of other smaller black holes can also lead to growth of black holes. So it's a more complex process than just looking at it in isolation. So one has to look at a holistic picture. So today, towards the end, hopefully there'll be a bit of time, and I'll tell you at least briefly results from the JWST, where they have been able to look at smaller sized black holes which seem to be rapidly accreting at very high redshifts and very large distances from us. And these are some of the most distant objects which we have been able to sort of observe, and not the most distant, but among the most distant. And one is beginning to speculate that these are the processes by which these supermassive black holes may actually develop. So one has to look at it more holistically as to how black holes actually develop and grow. Now, just to give you briefly, okay, let me see if there's one more question. Okay, fine. Now, let's look at just stellar mass black holes. I'll be a little bit more rapid, but I'll keep asking you questions in between, and you feel free to ask me questions as well. So if you ask me questions in between, then we can go a bit slower as well. Okay. Now, if you look at stellar-sized black holes, stellar-sized black holes evolved from the evolution of stars. If you look at the evolution of stars, then broadly, stars evolutionary paths are categorized into low or medium mass stars and the high mass stars. Low or medium mass stars will shed their outer envelope and end up as a remnant, which is called a white dwarf. Okay, and there will not be a massive explosion, and the white dwarf is, it could be about solar mass or so. But when you have a very high mass star, it ends its life as a supernova, leaving behind a compact remnant. So depending upon how massive the original star was, it could leave behind a neutron star, or it could leave behind a black hole. And the detailed sort of work of trying to understand what are the mass ranges, what are the mass ranges which lead to formation of neutron stars and black holes, that this is sort of a rough sort of sketch of it, that that it also depends a little bit on the constituents, etc. That if you take about 9 solar masses, the initial mass it starts off, till about 25 solar masses or so, you will end up with a neutron star. Okay, there's a dependence on metallicity as well, but we'll not get into too much of details. But just to give you a broad idea, so much more massive stars will lead to formation of a black hole. Okay, and and the remnant which it leaves behind over here is roughly in the ballpark of slightly over 2 solar masses or so. Okay, the most massive neutron stars are slightly over two solar masses or so, and beyond that you have the regime of the black holes. All right. Now, how did we actually find out about stellar mass black holes? The initial experiments were a lot of the discoveries in astronomy are serendipitous. I mean, people are brave enough, or and to ask interesting questions, build instruments, do experiments, and that really reaps rewards. And in fact, some of the early X-ray missions which were set up at MIT, they were there to they wanted to look at solar radiation. The sun was detected as an X-ray emitter as well, and from a solar corona particularly reflected from the light. And what they found was a very powerful source of emission called towards the constellation Scorpius. And this was a scan of the sky by a rocket-borne X-ray detector. It's among the brightest sources in the sky at extreme wavelengths. And initially, when SCO X1 was detected in the X-rays, one was not certain about what is the process which is responsible for it, what are the systems. But what one realized is that when more such systems got discovered, particularly Centaurus X3, and this is the constellation name, and this is an X-ray source, and this is 1, 2, 3, depending upon which is the number of the source that was discovered. This is the third X-ray source in the constellation Centaurus. Detailed observations were made by the Uhuru satellite. And when these detailed observations were made, you begin to realize that it was actually a binary system. How do you realize it's a binary system? One is that the X-ray emitter will get eclipsed by the star, and it needs to be at the right orientation as well for that to happen. And from that, you can go and estimate from the orbital parameters. You can go and estimate the mass of the mass of the. I've heard that we haven't found any hard proof of intermediate mass was to take more time than the universe existed, and how do we assume it existing after 1 billion years after the Big Bang? Okay, we'll come into that in a little while. We'll address your questions 8 in the end, because we will talk about intermediate mass black holes as well. Okay, now third X-ray source in the constellation Centaurus, and we can go and determine what the mass of the companion object was. In this case, it was a neutron star with a 1.21 solar masses, and the companion was a 20.5 solar mass object. Okay, the object which is accreting was a compact object. Now, how do we get the X-ray emission from these compact objects? It depends on two aspects of it. Okay, suppose we look at a binary system over here. Okay, they're broadly classified, although there's a wide range, into low mass X-ray binaries and high mass X-ray binaries. Okay, and the way the X-ray emission is generated is by accretion onto a compact object. I mean, if you look at a compact object, like a neutron star or a black hole or a white dwarf, so what happens is that as the material falls into it, potential energy becomes more and more negative, kinetic energy builds up, energy is conserved, and then it hits the surface. All right, in the case of a neutron star and black hole, so the kinetic energy gets converted into other forms, and it can generate a lot of energy via heat up the surface, generating a lot of energy, and given the temperatures, it radiates at extreme wavelengths. Okay, and the compact star, as I just mentioned, can be a neutron star, a black hole, or a white dwarf. In the case of a low mass companion, the companion star is less than about 2 solar masses, High mass X-rays are typically greater than 10. And as I said, there is a range, but this is sort of the broad classification. Now, all stars have a stellar wind. All stars have a stellar wind. Even the sun has a has a stellar wind, which actually affects our space weather as well. Just recently, there were coronal mass ejections from the sun, which lit up beautiful aurorae in the northern hemisphere, and there were a lot of pictures in the social media. Okay, these are charged particles which are accelerated by the magnetic field of our galaxy. Now, what happens is that the more massive the star, there is a stronger stellar wind, and in the case of a high mass X-ray binary, most of the accretion of matter is from the stellar wind over here. Okay, and if there is a neutron star which has a strong dipolar magnetic field, these particles will actually get accelerated towards the poles and give off radiation. And this radiation is usually in the X-ray region of the spectrum. Whereas in a low mass X-ray binary, during the course of its evolution, this can evolve into filling up the equipotential over here, which is called a Roche lobe, and it will escape along the Roche lobe. This point is called a Lagrangian point, and form a hotspot or an accretion disk around the companion compact object over here. All right, and the highest luminosity that you can get over here from these objects is what is referred to as the Eddington luminosity. Now, what determines that? Because what is happening is that you can see the radiation that you're getting or the emission that you're getting is due to accretion of matter, either via the Lagrangian point or via the stellar wind that it is accreting onto this compact object. But what is happening is that when you also generating radiation, that radiation will also exert a pressure. Radiation pressure, usually because the material is ionized, it is due to Thomson scattering of the photons with the electrons. And if you balance the radiation pressure with the effect of gravity, then the maximum luminosity which you can get is in the ballpark of 1.3, say, into 10 to the power of 38 m upon m sun erg per second. So for a 1 solar mass object, it will be about 10 to the power of 38 ergs per second. So X-ray luminosity is typically in the region of 10 to the power of 36 to 38, and it will depend on the mass of the accreting object. So it is consistent normally with the maximum luminosity that you can get. And when you do the detailed dynamics, you can using Keplerian motion, etc., that work out masses of the two objects, and you can find evidences of black holes. And these are just three examples which I've given in our own galaxy. Accreting black hole is about 10 solar mass, 21 solar mass, and this one there's a limit. It's much easier. It's easier to do that when it is an eclipsing one, but otherwise also you can go and make models for it and try and get estimates of the masses. Some of these accreting systems also spew out jets, and which I will not, I'm already 12:24, I have a long way to go. So I will not get into details about that, but these are the sort of stellar sized black holes. Now, if you go for intermediate mass black holes, which Zaid asked me a little bit about a little while ago, that it is still debated in the literature, but there is more and more increasing evidence that the gap is getting sort of filled over, typically over 100 solar masses till about 10 to the power of 5 or 10 to the power of 6 is what we call intermediate mass black holes. And I will just show you a few examples without getting into the nitty-gritty of details of how it is estimated, of some of the lines of observational evidence that people have taken, astronomers have taken over the years. One is that when there is an X-ray binary and matter is being accreted and it moves around, one often sees what are called quasi-periodic oscillations. Okay, and as I mentioned a little while earlier, the orbit, the Schwarzschild radius, and the inner glass stable orbit depends on the mass of the black hole. So these quasi-periodic oscillations, as they are moving around, also depend on the mass of the black hole. And this is what you see over here is an event where is the black hole mass is plotted against the quasi-periodic oscillation frequency. Okay, frequency would be inverse of the time period. All right. Now, for example, the stellar-sized black holes, you'll remember 2gm upon c squared. So mass is small, And you'll get, for low mass black holes, these are stellar sized black holes, you'll get a larger frequency over here. When you go to larger and larger mass black holes, you can see that the quasi-periodic oscillations will go lower and lower. So there have been quasi-periodic oscillations seen in a number of objects, and not only number of objects which are in binary systems, but in the case of active galactic nuclei, what also happens is that if an object goes, if a star gets within a certain distance, a tidal disruption sort of radius, then it can be tidally torn apart, and that material will also get accreted onto the black hole. And you can see the tidal disruption events as an increase in intensity of light, flash of light, which will decay slowly. And these signatures have been imaged, and there are many tidal disruption events which have been seen. But there are also objects, astronomers follow up, trying to detect quasi-periodic oscillations in these tidal disruption events. And I'm just giving you one example which appeared earlier this year in Nature Astronomy, where the mass is about 9.9 into 10 to the power of 3 to 1.6. So you can see it's about roughly in the ballpark about 10 to the power of 4 solar masses, which is in the range of intermediate mass black holes. Okay, and I mentioned to you about the inner stable orbit also depending on the spin of the black hole, and these are actually two lines which they have drawn depending upon the spin of the black hole, and from that you can also try to infer what is the spin of the black hole. Okay, and this has also been done for a number of objects. I've just quoted one particular paper over here. Besides looking at quasi-periodic oscillations, the other thing is to look at hyperluminous X-ray sources, which may be radiating at much more than the which are extremely luminous compared to the general population of X-ray binaries that we are aware of. So this is one such example where HLX is a hyperluminous X-ray source. It's about 10 to the power of 42 Ergs per second. This is an edge-on spiral galaxy, ESO 243 minus 49, and there's no optical counterpart for this particular source. It's usually variable, and from the luminosity, they have tried to estimate. It's a bit model dependent, obviously, but from the luminosity of the object for which could be responsible for these hyperluminous X-ray sources, and this particular piece of work, which was estimated a mass of for this object, about 500 solar masses or so. So you can see it is higher than the kind of range of 500 that we talked about. Other objects go to higher masses as well. But the more convincing kind of estimate would be if you can actually measure motion, right? And try and look at it motion around a point-like object and see if you can find emission from such point-like objects, which are much more than the stellar mass black holes. So these are molecular gas streams, okay? Molecular gas streams orbiting around an invisible massive object towards the central region of our galaxy. So you'd know from your basic physics that molecular lines have quantized energy levels. This is from total angular momentum, the 4 to 3 transition, which occurs at a frequency of, I think it is about 340 something gigahertz, 345 gigahertz. So these are at millimeter wavelengths. So what the Japanese group did was they imaged this with this was at ALMA, and looking at the kinematics of different molecular line-emitting gas towards the central region of our galaxy is carbon sulfide. This is HCO. Okay, and this is hydrogen cyanide, HCN. And around a single point mass, they estimated a mass of about 3.2 into 10 to the power of 4 solar masses. So there seems to be, this is not exactly the center of our galaxy. It is about 100 times smaller than the central black hole, the supermassive black hole, 10 to the power of 6 solar masses in the center of our galaxy. So is there a population of wandering intermediate mass black holes in our galaxy? I mean, this is one example of it, but one needs to sort of extend this further and look at more of these, and to be really able to answer the question whether there is a population of intermediate mass black holes. The other aspect is globular clusters. Globular clusters are collections of thousands and thousands of stars, and this is one which is one of the most massive globular cluster in the M31 system. goes by the name of B023-G078, and using very high resolution, because you need high resolution to be able to not only spatially but also spectroscopically to look at the kinematics of the velocities that in the globular cluster, to see if there's any systematic motion, and model it in terms of the stellar dynamics, and see if there is a black hole component or suggestions for a black hole component. And what this group did, Pachiti et al., which was published in Astrophysical Journal some years ago, of this particular object, there's been more such objects which have been studied, is that they from modeling of it, they infer a black hole mass of 19.1 into 10 to the power of 4, which is, and the whole entire mass of the globular cluster is about a few million solar masses. So it's a very small component, but you can see that there is sort of systematic rotation also, and there is also increased velocity dispersions towards the center. So this is another sort of example of intermediate mass black holes. But the other evidence for intermediate mass black holes of over 100 solar masses has come from the detection of gravitational waves. Okay, I'm going a bit slow, so I will not get into too much of details of gravitational waves, but just come to the results. Okay, but gravitational waves are basically ripples in space-time, as all of you would be familiar with, and these are caused by gravitationally accelerated bodies. And this is a prediction of Einstein's theory of gravity. Einstein himself, initially was skeptical about it, but it is a prediction of his theory of gravity. And let me not begin with details of gravity waves over here, but just to give you the kind of frequency that one is talking about, it's a huge range from about 10 to the power minus 16 hertz to 10 to the power of 4 hertz or so. Binaries, supernovae, and pulsars, etc. But it goes down to much lower frequencies, which means much larger wavelengths. Electromagnetic waves, where we typically observe, is about 10 megahertz, which is 10 to the power of 7 hertz, which is the lower end of the radio window as observed from Earth, because the ionosphere cuts us off. But if you had to go to even lower frequencies, you have to go to the moon. And any accelerating non-spherically symmetric mass can emit gravitational waves. Okay, so this is what we will see. And these gravitational waves can be very long wavelength waves. And that is why you need these huge interferometers extending for kilometers and kilometers. Okay, just to give you an idea, if you had a binary system with an orbit of 1 hour, okay, the wavelength, if you calculate from the period, okay, frequency of gravitational waves is twice the frequency of the orbit, then you'll get a lambda wavelength of the gravitational waves, which is about 5.4 into 10 to the power of 13 centimeters. Okay, you can see that it is much, much larger than the diameter of the Earth. The diameter of the Earth to the wavelength is a tiny fraction. And the rate of energy loss, which you look at it, just to point it out, is inversely proportional to a to the power of 5. A is a semi-major axis. So the release of gravitational energy is much more rapid as the two objects coalesce. So if you have an object which is just symmetrically, perfectly spherical and it's just oscillating up and down, you're not going to get gravity waves. But if you had an asymmetric body which is rotating, or an asymmetric explosion, or a binary system, then you're going to get gravitational waves. So this is the first detection of gravitational waves. GW 150914, where two black holes of 36 and 29 solar mass formed to form a final mass of 62. So this is still in the regime of stellar mass black holes, okay, if we consider 100. But as we move on, we find that we are entering into the regime of 142 solar masses, which is in the intermediate black hole mass range. And today, what has happened is that more accurate, they've also fine-tuned, they've improved their instruments. And this is just a comparison of two detections, okay? GW 150914, you can see that, you can see it, but you can see today the signal is much, much stronger. And with a stronger signal, during the ring down period of the merger. So they sort of get closer and closer, they merge, and then there's a ring down period, and there is a more massive black hole. Okay, that you can also, because that will also depend on the spin. So people are, sort of working on trying to determine spin as well, mass as well as spin from these black hole estimates. This is not the most updated picture, but you can see that, stellar mass about 200 or more than that is what is shown in this picture, close to 200. A recent paper in the Astrophysical Journal Letters talked of looking at the combined data that there are 110 to 350 solar masses. So we are sort of, there's increasing evidence that there is evidence of intermediate mass black holes. Now, in terms of gravitational waves, what is happening is that from earthbound systems, one has been able to look at till about a few hundred or so. But if you need supermassive black holes or much more massive black holes, even intermediate mass black holes, much more massive intermediate mass black holes, you're going to get longer and longer waves. And pulsar timing arrays are the way that one is trying to detect them. A few years ago, that the nanohertz gravitational waves were reported. It's at a 3 sigma level, but the different timing arrays, the Indian pulsar timing array, the Chinese, the European, the North American, they're all trying to put the data together to try and get more data, and also the Australian, and try and improve the signal to noise ratio. And these would be signals from the mergers of supermassive black holes, or even in the slightly lower level, the intermediate mass black holes. But for gravitational waves, we are also entering the regime of intermediate mass black holes. Okay. Now, to go back a little bit more into supermassive black holes and the extraction of energy from it. So you can see that we talked about the Eddington luminosity, which is the maximum luminosity that accretion onto a compact object can achieve by balancing the radiation pressure with the effect of gravity. And it was 1.26 or roughly about 1.3 to 10 to the power of 38 ergs per second. So you can see that if you assume the similar kind of okay, we'll come to, there's few questions. Excellent. We'll come to that in a little while. Okay. We'll come to that in a little while. Okay. Then to the power of, you can look at the luminosity over here. For example, if I take a luminosity of about 10 to the power of 46 ergs per second, and the energy is by accretion onto a supermassive black hole, then, just by looking at the Eddington equation, I would have to have a black hole mass of about 10 to the power of 8 solar masses or so. All right. And again, what we want to do is try to understand the energetics, or a total energy content, energies, and these energy output from these point-like objects from the nucleus of these active galaxies. And the best way seems to be via accretion onto supermassive objects. And one might ask the question that, for example, in the case of a neutron star, or a black hole, neutron star, or a white dwarf, there is a hard surface to which the material which is accreted falls into. But what happens in the case of a black hole? Okay, what happens in the case of a black hole? I haven't asked you for a question for a long time, so let me ask you now. So, what do you think happens in the case of a black hole? Because it's a singularity, and you're accreting material, and it doesn't have a hard surface. Anybody?
So can you repeat the question once?
I said that accretion onto a compact object, because as you get closer and closer into a more compact and massive object, the gravitational potential energy gets converted into kinetic energy. Object is more tightly bound, the kinetic energy increases, potential energy becomes more negative, and then it hits a hard surface. And that energy which is built up, the increased kinetic energy, comes to a halt over there. And the energy gets converted into heat in other forms, and you get emission from it. Like, for example, X-ray emission from the surface of a neutron star, okay, or a white dwarf, which may be accreting. But in the case of a black hole, we don't have a hard surface. We have a singularity. So if a proton is falling into a black hole, it should just fall through, go beyond the event horizon, and you should not get radiation out of it. So what is it? How is it that we get energy out of a hotspot in these energy out of a supermassive black hole in these active galactic nuclei?
I think the falling particles rub against each other while falling, and it is the friction between them that causes this radiation, because I don't know about quantum radiations at all. So that would be my guess.
Yeah, I mean, you're right. You're right. You're right to an extent, but I was looking for a particular term. Anybody else wants to add to Indra-Sis's answer? Uh,
Is it the
So does it
Penrose process?
sorry.
Is
does it
it the
contribute to the rotational energy of the black hole?
Okay, Pranjal, we'll put everything together. Basically, what happens is that when material is being accreted, Pranjal and Indra-Sis, they both gave the answers, but we have to combine them to get a complete answer. Is that when what we talked about earlier, when we talked about the structure of the black hole, we talked about the photon radius, we talked about the singularity, we talked about the Schwarzschild radius, we talked about the last table of it. But beyond that was the accretion disk, right? So because material comes with a certain angular momentum, usually that 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 along the rotation axis, actually they would collapse, and perpendicular rotation axis they will form a disk kind of structure. So in the disk, they interact with one another, and the viscous dissipation of energy along the disk is what gives rise to a lot of the emission that we see. But the other aspect is also there, that now, for example, we have these jets which are spewing out. Today, we have not talked much about jets for shortage of time, and these are also being supplied with energy. Then there's also uh, material which are in the vicinity of the black hole, often referred to the corona, which is also getting heated up to very high temperatures. Now, there are also processes by which energy can be extracted from the rotational energy of the black hole, and that is another aspect of it. Okay, but if you tell me that viscosity or interacting with particles, rotation, accretion disk, etc., that will also satisfy me, because that is the primary process that one is talking about in terms of a lot of the energy that one sees from the vicinity of the black hole. But formation of jets and all that, one also extracts rotational energy. There were processes which are being worked out by Roger Blandford and his collaborators at Caltech, but we will sort of move on. But Indra-Sis and Pranjal, I think both your answers together provide a reasonable explanation as to why we are talking about to explain the energy output from these. Okay. Now, to just talk about jets a little bit, these are images which we made with the GMRT, and these are giant radio galaxies. This was one of the largest ones for till recently. Till the LOFAR telescope in Europe detected even larger ones. And a black hole, this is one where we think that the jets may be processing. This is where the energy supply probably gets cut off and restarts. So you see two pairs of lobes. But the total energy in these lobes is huge. Is huge. There's about 10 to the power of 60 ergs or so. So there's a huge amount of energy which is stored in the lobes, which originate in the nucleus of the galaxy, and that is believed to be due to the accretion process. Okay, and I mentioned to you a little while ago about just the Schwarzschild radius and just the Eddington luminosity giving us an estimate of the black hole mass, because when you have a luminosity of about 10 to the power of 45 ergs or so, 46 ergs, to generate that kind of luminosity by the most efficient process that is known, you need very massive objects to be accreting matter. But there are other ways also where people have tried to, get a first glimpse of what the masses could be before one was able to directly measure them. And I'll just very rapidly go through them. This is just, Keplerian motion over here. And if you take the emission lines of objects, that is, and have an estimate from where they are originating, you can go and estimate of the mass. Now, how do you get an estimate of the velocity? As one of you, I think Indus has mentioned early on, that the velocities could be due to Doppler motion, and if you have Doppler motions of 1,000 kilometers per second at a distance of about 10 parsecs, then you will be able to get an estimate of the mass. Now, how do we get an estimate of the mass? of the distance from which from which the lines are emitting. I will just tell you that briefly. Maybe causality arguments, I'll leave it for today because we're running out of time. But what we can do is we can measure the variability in the line uh, compared to the variability in the continuum. So let me just spend half a minute on that, okay? For example, we mentioned that due to the effect of the black hole, the lines are broad, okay? And the lines are also energized by emission photons from the vicinity of the black hole. Now, what happens is that if there was no change in intensity of light from the vicinity of the black hole, then the lines would be steady. They would not actually vary very significantly. But if there is a sudden change in intensity for whatever reasons, okay, then the line would also change. So what people do is they monitor the continuum light which comes from the vicinity of the black hole and monitor the line intensity as well. And you will find that the line intensity lags the continuum intensity. It comes later. And why does it come later? Because light takes a certain distance to travel to the region from which the emission lines are coming. And this whole exercise is called reverberation mapping. So from the delays, by carefully modeling it, you can find out how far the object is. And from that, you can go and estimate what the mass of the black hole is. And somebody, I've just quoted a number, but this is a very rough number of 10 to the power of 9 solar masses or so. Okay. But you can do more. Of course, today for M87, we have direct images of the vicinity of the black hole. We can model that. But otherwise, you can look at gas motions as well as stellar motions to look at uh, evidences of massive objects in the center of galaxies. This was early days of the Hubble Space Telescope, when HST images showed gaseous content right in the center, and you could go and look at the velocity shifts of these lines, and from the velocity shifts, you know how rapidly they are moving. And from how rapidly they are moving, you can go and estimate what is the object at the center which is responsible for their motion. So this one was for another galaxy, M84, and about 300 million solar masses. You can do this for different kinds of objects. For example, over here, what has been done is that there are maser spots. The maser spots are usually water vapor, etc., and they give emission at millimeter wavelengths at radio frequencies, and you can image exactly where those points come from in the center of the galaxy using very long baseline or high resolution techniques. And then what you can do is that because the line will get shifted, you can also see whether it is red shifted or blue shifted. So a particular point, a maser spot, which you can image with very high resolution, then you can also know its exact location, because you not only have high spectral resolution, but you also have high spatial resolution. And when you do this, you find that in this particular galaxy, NGC 4258, all the points lie in a warped disk kind of structure. You know exactly where they are from the center. You know what velocity they are moving, and you can go and apply Kepler's laws of motion and get an estimate of the black hole mass over here. So this is something which has been pursued for other galaxies as well. And of course, in the case of our own galaxy, what has been done is actually following the motion of stars in the center of our galaxy. Now, I mentioned earlier on that because of the interstellar medium, it's very difficult to see the center of our galaxy. So, how is it possible that one has been able to infer the mass of the black hole by looking at the motions of stars in the center of our galaxy? So, any one of you can unmute and unmute and answer. Some of you would have sort of seen a similar picture, but what do you think? Optical light
Uh,
gets completely obscured. Yeah, go ahead, Indra.
Sorry, Professor Saikia, can you repeat the question once again? I probably
no. Okay. I'll repeat the question. Okay. Now, earlier on, when I talked about the interstellar medium, and one of you had talked about radio waves, I mentioned that the center of our own galaxy is very difficult to see at optical wavelengths because of obscuration and scattering of light, visible light by the interstellar medium of the galaxy. Okay, but yet two groups have been able to look at the motions of stars in the center of our galaxy to infer that they're moving around a supermassive black hole. How do you think that is possible?
uh, I think uh, if we just consider modeling them, then without a very massive object, the predicted motions would have been different. But when you consider a very massive object at the center, then probably the model predictions might have matched with what they saw. So so that would have been an indirect observation, the supermassive black hole.
Interesting. What you have said is absolutely correct. But what I was trying to get at is how is it at all possible to observe these stars?
Oh, okay. Yeah,
Okay.
sorry.
I mentioned about radio waves coming through, but these are stars. Radio waves, long wavelengths, suffer very little, obscuration. They would come through, whereas visible light is very difficult to see because, me scattering scattering would actually affect light that is coming from the center. So it's very difficult to see stars, but yet these people were able to do it. Okay, let me. I mean, this is a sort of, I mean, if you're not familiar with it, it's difficult. But what you've said, Industries, is absolutely right. So what you have to do is, as I was saying, that long wavelength light comes through, but stars are very poor emitters at radio. But if you take the temperature of a star, for example, our star is about, whatever, 6,000 degrees Kelvin, and if you apply the lambda Wien's displacement law, you'll find that it radiates. The maximum emission is in the optical region. Okay, it peaks in the optical region of the spectrum. And if you had much more massive stars, then they would actually have even higher surface temperatures, and they would, peak in the ultraviolet region of the spectrum. But if you had cooler stars, then they would begin to radiate in the infrared region of the spectrum. So longer wavelength, just like the long wavelength sunlight, the sun appears reddish in the evenings or mornings. The reddish light comes through without significant scattering. Similarly, if you had cool stars, where the emission sort of peaks at longer wavelengths, you'd be able to see them. All right, but there was a huge challenge in trying to measure these accurate positions, and that was something which was for which Andrea Ghez and Reinhard Genzel got a Nobel Prize for Physics in 2020. And by looking at the motions of these objects and trying to infer the mass, and as Indus mentioned, it was careful modeling of the motions of the stars that led to an estimate of a few million solar masses for the center of our black hole. Let me see. I think I'm exceeding by a bit, so I'll actually leave some of these things. This is what I've already explained to you earlier. Okay, these are, yeah. I mean, we have more measurements. Okay, I'll leave some of these aspects out right now, but you've got a fair idea that of how black hole masses get estimated. I'll just delve 2 minutes on this because that is another new technique. Okay, which one has used in the estimation of black hole masses, and also in some cases try to estimate spin as well. Now, this is an object which is a disk around a black hole, say a supermassive black hole. Okay, and what you see over here is the colors which have been able to denote is due to the motion or the velocity of the disk which is rotating around a supermassive black hole. If you look just at Newtonian physics, all right, and the disk is sort of stationary, this is what you would get. Emission along these directions would add up and is optically thin, say, and you would get a shape of say a particular line. This is the iron K alpha line because the temperatures are such that this iron line is visible. This is what you would see, the particular line. All right. particular line from these two regions. Now, if you put in special relativity, then what happens is one side which is approaching you gets Doppler boosted, slightly shifted in frequency, and the other side which is moving away from you gets Doppler diminished. This is just a special relativistic effect. All right. And this, so one side gets boosted up, the other side gets diminished. Now, then you bring in general relativity effect, where gravitational redshift comes into play, and the gravitational redshift is more intense towards the central region, okay, the central region. And if you shift the whole thing gravitationally, then this is what you will get. And this is the line profile which you ultimately get because you don't have the resolution to really see from which side of the disk it is coming. These are all unresolved. So you see an aggregate spectrum which looks like this. All right. Now the shape of the line if you had adequate or good observations, can also help you try and estimate properties of the supermassive black hole. Don't worry about the detailed fits to the lines, but just as long as you remember that one of the very prominent lines, or one of the important lines at X-ray wavelengths, comes at 6.4 kilo electron volts. Is an iron line from the K level, level, and from a detailed modeling of the profiles, you can try and see whether it is what kind of a black hole it is, whether it's rotating, the mass, and what is the spin of the black hole. So this I've already talked about, so I'll skip the supermassive black hole, okay? I'll skip the supermassive black hole. I mean, if you want to just see a motion picture, I'll just show you this for a little while, and then we'll stop. So this is year after year after year they kept modeling, and you can see the year on the side over there. And this S02 is really interesting because it went very close to it and completed an orbit as well. Because you could have argued that, well, from these observations, that how do you know it's not just a very massive globular cluster kind of object, a lot of stars which are over there. But this got so close that, no such object would have actually fitted the bill. And it completed a full orbital period, okay, in about 16 years or so. So these are the kind of observations, and you need not only for the light to come through, but to get accurate measurements, you need very high angular resolution. So this was achieved with the help of adaptive optics, where they could get resolutions as to the atmosphere didn't bother them, by these two groups led by Andrea Ghez and Reinhard Genzel, who got a Nobel Prize in Physics for this. This is just another simulation. Now, I'll spend just 2-3 minutes talking about the growth of black holes. This is one of the questions which was asked, okay, right in the beginning. And I'll talk to you just to highlight one result from the JWST, that the growth of the black hole seems to go along with the growth in the bulge of the galaxy, okay? For example, our Milky Way 2, it has very prominent spiral arms, but it has an inner bulge over here, okay? Now, as the mass of the central bulge increases, so does the black hole mass over there. So these are two properties of a galaxy which are intimately related. For a galaxy which looks elliptical, the entire elliptical galaxy is the bulge. Whereas in a spiral galaxy, you have a bulge as well as a disk, and the disk contains the spiral arms. Okay? So you can infer the mass of the bulge from the velocity dispersion as well. So some people plot the velocity dispersion rather than the mass of the central bulge, as is done in this figure over here. But this is actual data for a whole range of galaxies for which it's been measured. And this actually tells us a little bit about how black holes may have evolved. For example, when you look at an elliptical galaxy, which are usually more massive than that of a spiral galaxy, one of the ways an elliptical galaxy can form is by the merger of spirals. And we know that from simulations as well as from observations. It takes billions of years for that to settle down. But we have observations of objects which are at different stages of merging. Just as you can, if you take a snapshot of a population, you'll see babies to elderly persons, and you can try and infer that babies grow up to older persons. Similarly, when you look at objects at different stages of mergers, you can try and find observational evidence of spirals merging to form elliptical galaxies. And these are also being numerically shown by putting into physics of mergers, of how things can happen due to the gas as well as the stars interacting with one another. So black holes, this is a more recent picture, but this also is not the most recent picture, with the black hole mass and the bulge properties are very closely related, but not with the galaxy properties as a whole. So these are important clues towards understanding how galaxies may have evolved. Now, to come back to the question about how about the rapid growth of black holes right from the early stages of the universe, these are very recent results from the JWST 2024-2025 and interpretations of it. So these are what are referred to as the little red dots. Okay, they are small galaxies. They're small galaxies, and they have tried to estimate the masses of the black holes that reside in these galaxies. Now, how do you estimate the mass of the black hole over there? Okay. Now, these are very far objects, very distant objects. You can just see them that they're reddish over there. And they have done that by looking at the widths of the line profile, assuming the widths to be due to rapid motions of gas, as we talked about earlier. And when you do that, then one group actually estimated a mass of about 10 to the power of 7 to 10 to the power of 8 solar masses. Another group which tried to find other reasons for possible reasons of scattering for line broadening, and came up with lower estimates of 10 to the power of 5 to 10 to the power of 7. But you can see that some of these are in the borderline of intermediate mass black holes and supermass black holes. Now, the reddish color is ascribed to, these are occurring in very gaseous environments over here. And also these objects, given their luminosities, they seem to be accreting very rapidly compared to objects which are more evolved and more recent and closer to us. Okay, so these may be providing clues. We are still in the very early stages of understanding these little red dots, as they're called, in terms of trying to understand the growth of supermassive black holes. So perhaps rapid periods of accretion plus coalescence of black holes in the vicinity. For example, we found evidences of randomly wandering black holes in the vicinity of our own galaxy. It will be very difficult to try and get such estimates for more distant objects, but at least it gives us a framework to work on to try and understand the formation of more massive galaxies, both by accretion processes as well as by coalescence of smaller size black holes. So looking ahead, just a list of questions. We are getting more and more idea of the demographics, particularly JWST has opened up new windows. Then how do massive supermassive black holes form? We are getting some clues. How do they evolve? And greater understanding of the close relationship with galaxy evolution, both from modeling as well as further observations. I didn't talk about magnetic fields today and the behavior of gas and magnetic fields in regions of intense gravity, jet launching, and physical properties. What physical properties of black holes determine the power of jets? So these are aspects which are still at the frontiers of trying to get sorted out from both theoretical work, simulations, as well as observational work. So I think I'll stop at that and take a few questions, and then we can. Okay, let me try and sort of look at a chat box for questions which I missed. Okay. I've heard that, okay, Zaid has talked about intermediate mass black holes in more time than the universe has existed. Then how do we are existing after 1 billion light years from the Big Bang? Okay, I mean, as I just talked to you about, this is something which one is trying to work on, and we have examples of massive black holes very early observationally, if our interpretation of the broad lines is correct, because even by conservative estimates of the width of the broad lines, we have pretty massive supermassive black holes quite early on in the universe. So I think we have to, traditional ideas of galaxy evolution and black hole evolution are being revisited. And I think at least there seems to be some suggestions that these are going through a period of very rapid or very strong accretion, which may be contributing to their growth as well. But this is something which I think we will learn a lot more as JWST observations continue, and we have more inputs from studies of these sources from other wavelengths as well. For example, these red dots, although one is talking about black holes over there, there's hardly any radio emission from them. So limits on radio emission is extremely weak. So then why aren't they actually having jets over there? Although we know that some kind of jets exist in, intermediate mass black holes as well. Today we have collimated structures which are seen in dwarf galaxies in our neighborhood as well. Okay, GC 4395 being one prominent example. Okay. Can this megaverse be considered as carousel, the main rod, as some great power at running the megaverse, and each horse is each universe, and each universe is again a carousel? So megaverses is something, mega universes or multi-universes is something which I haven't talked about today. Okay. Okay. Hawking's radiation also we haven't talked about, because I think today's focus is on observational evidences about it. So we haven't talked about that. Particles, ergo particles. Yeah, actually, the Penrose process could play a role in the evolution of the black holes. Stavia, that is correct. Explain super Eddington accretion. Okay, super Eddington. Okay, I just. Okay, for black holes to, for these kinds of black holes that we talked about, the time scales are, just doesn't match for disappearance by Hawking radiation. That's not going to happen. But let me just look at this other question: super Eddington accretion. So let me just try to address that a little bit. Okay, try to address a little bit, because what is happening is that when we are talking about the Eddington luminosity, the calculations which we do, that we are assuming that that matter is being accreted spherically, and also that radiation is being exerting it uniformly in 4 pi steradians, and we are trying to balance radiation pressure with the effect of gravity. Okay, now can we beat this process? Can we have emission which is where this is not the case? Okay, now for example, if accretion is onto a disk and there is an efficient way of extracting that energy out, okay, in principle we could probably have that, because radiation pressure is not acting in all directions. But radiation pressure, we could probably have that. But observationally, when we look at the luminosities of both black hole binaries or supermassive black holes, or the luminosities of AGN, they generally seem to be consistent with the luminosity which is set by the Eddington limit. And so I think beyond that, I mean, I don't think there's much to say. Because observationally, what we find is that objects are generally within the Eddington luminosity if we actually calculate the distance and the flux which we see. Let me just check this up once more. Okay. Okay. So as I said, I think, I mean, if for some reason you can get matter which is falling in more rapidly, the radiation pressure is not acting on all the matter, then you could, in principle, get super Eddington luminosities. But observationally, we don't see much evidence of that in almost all the objects. Okay. So let me see if there's any other questions which you want to, some industries has his hand up. Is it from before, or you want to?
No,
If
I
someone
just
has,
wrote it.
sorry, no, you
If
can,
I can go ahead. Uh,
sorry,
Sorry.
can I go ahead with the question?
Yeah, you go ahead. Go ahead.
yeah, go ahead.
Yeah. Thank you for the talk, Professor Saikia. This was really interesting. And I mean, I did not see how the time passed. My question is mainly regarding, not related to this presentation, but I would like to ask a more bibliographical question. So for someone who is just, I mean, accustomed with partial differential equations and its first course and multivariable calculus, can you suggest some references, especially mathematics references, which would enable understanding of general relativity uh, and in the future, if someone wants to take it up? So I have always felt that, I mean, I could go through popular presentations like these or YouTube videos, but I don't have a theoretical grasp of the maths behind it. So if there are some good references which I could follow to understand mathematics references to understand general relativity in the future, I mean, so that would be dealing with curve geometry. Can you suggest
Okay.
some?
Okay. Actually, I mean, when I first studied general relativity, the book I studied from was Steven Weinberg and Jain Nadikar's books, because I think
Okay.
they also give an observational or sort of physical intuition of what we are dealing with, rather than just pure math. These are two books which I studied when I was studying general relativity. I mean, today actually I work much more from an observational perspective. I don't do hardcore theory, but when I was, I mean, I delved into Misner, and Wheeler as well. But my main sort of books were Steven Weinberg and Jayant Tandikar.
Thank you, Prof. Saikia.
Yeah. So, Indranil, have you had a look at these two books by any chance? Hello? Have I lost connection or what? No.
No, sorry, my mic.
Okay, okay. Two participants raised their hands. Okay, Vaidik Saha, you can unmute and ask.
Hello, sir.
Yeah.
Can you please explain the baby universe hypothesis?
Actually, I don't know much about the baby universe hypothesis, to be honest, So I won't be able to tell you much about the baby universe hypothesis. I mean, my work or study has largely been in the observable universe. Okay. And the observable universe, I mean, there are solutions which will give you multiverses or multi-universes, but the observable universe is something which I deal with or I study. So I wouldn't be able to tell you much about the baby universe, Vedic.
Okay, sir. Thank you.
Okay, Zaid.
Yeah, we take last question.
Okay.
So, sir, I had a question about Hawking radiation. So if black holes dissipate all of their mass through Hawking radiation, what will happen like at the end of its lifetime?
See, you have to look at the time scales of Hawking radiation. Hawking radiation may be relevant for very small black holes, but for all these, the time scales are irrelevant actually.
Okay, so sir,
Yeah.
one more thing, the what happens to the singularity? You can say like after.
See, yeah, the thing is that any singularity is not a very satisfying solution, right? Whether it be the
Yeah,
origin of the universe or the point of a black hole.
yeah,
But today, actually, there is a lot that we can understand in terms of the formulation using Einstein's general theory of relativity and postulating a black hole as in Einstein's theory of relativity, and understand the physical universe and understand the constituents of the physical universe. But one hopes that one will be able to understand this without singularities. But singularity per se is not you know but the black hole is, today as we understand it, it's a point, it's a singularity which is charge, mass, and angular momentum.
yeah. Thank you, sir.
I just wanted to say to all participants that we've shared a really small feedback form. So kindly do fill it and give us any more suggestions for either this talk or for future events that Isaac may. I'll put it in chat. And there's a few more questions. I'm not sure if we have the time to take them, but you can look at the chat. There's two more questions if you can.
Okay, I'll try and do that. Okay, if we have two black holes orbiting each other, is it possible to see changes in our observational spectra, just how we see binary stars? Yeah, actually, we can. In fact, by looking at okay, let me put it this way, Hamza, that in the case of stellar mass black holes in the binary systems, you can actually see the lines shift in reasonable time scales. But when you have massive black holes, the changes will be on much longer time scales. But you should be able to see similar lines which are displaced in velocity, because if there are two black holes which are orbiting one another, and they have their own system of emission lines, and one will be blue shifted, one will be red shifted. So you should be able to see emission lines in binary black holes. And in fact, people tried to infer the existence of binary black holes by looking at these line profiles. Okay, and some of these candidates were later followed up also with radio observations to see actually if you can confirm that they are indeed binary black holes. There are several very tantalizing examples which are possibly binary black holes. And this is a way of actually trying to identify or look for them, but you'll not see the kind of motion which you see in the case of stars which are moving about one another. Okay, the time scales will be very different. Okay, let me see. And how does stellar wind? So can you please explain in slightly more detail the Roche lobes and how does stellar winds also come into the picture? Okay, let me try and explain that. Okay, now for example, if you have two massive objects, say of M1 and M2, you can draw the equipotentials over there. Okay, equipotentials over there, and that would be true. For example, the Sun Earth system, any system which you can take. Okay, and the points where the potentials are different in the particular examples which I showed, that is referred to as the Lagrangian point. Maybe I can try and show the picture. Let's see. Let me just sort of see if I can find it. 1 second. Okay, 1 second. I'll have to probably close this and then do it. Just 1 second. Okay, you can still see my slides, right?
Yes, sir.
Yes.
Let me just see. Here it is. Okay. Here it is. Okay. Now, I'm not putting it full screen, but I hope it's okay. See, so these are the lines of equal potentials. All right. Equal potentials. Now, for these two stars, of these two systems. Now, in the case of a low mass star, okay, in the case of a low mass star, the stellar wind is not very strong. So the only way that material from the companion star can fall into the compact object is if the material comes to the point called the Lagrangian point, where the potential from this star and this star is the same, and the gravity of this compact object, and the fact that this star is actually expanding out, will draw this material into the surface of this compact object. All right, and it could form an accretion disk, and from which material will keep falling and gets heated up, and you'll see it in X-rays. Now, in the case of a massive star, it has a very strong stellar wind. The more massive the star is, the more luminous it is, and the more luminous and massive it is, the stellar. So what you see over here is that accretion can take place onto a compact object by just trapping in the material which is actually coming out from this massive star as a stellar wind. And in the case of, for example, if it is a pulsar, if it a compact object with a strong magnetic field, particles will actually be accelerated along the magnetic field lines over here. So even without filling up the Roche lobe, the strong stellar winds will be captured in the case of this high mass X-ray binaries. Whereas in the low mass X-ray binaries, the stellar winds are very weak relatively, and material actually flows in because of the overflowing of the Lagrangian point. Is it all right?
Yes, sir. Thank you, sir.
Okay. Okay, Hamza. Okay. Somebody asked about the Penrose's work being true, making black holes doors to different universes and dimensions. I would say that I'm not very familiar with with the kind of theoretical work on of Penrose and multiverses and those different universes. My work and understanding has largely been confined to the observable universe, which I largely work on and deal with. Subhash Hegde says supermassive black holes in the early universe formed a high rate of merging of small black holes. This could be one of the reasons. Formation of black holes very near to each other in the early universe. Okay. Now, for example, the thing is that if you want to form a black hole, the most easiest way is the massive stellar sized black holes. Okay, if you had very massive stars which are forming, and they would evolve very rapidly. Today, in our own galaxy, for example, we have black holes which are we have stars whose masses we infer to be 2 to 300 solar masses. So we could have very massive stars forming whose lifetimes will be very small, and they'll leave behind black holes at the end stages of the evolution. Their lifetimes will be short compared to the higher the mass, the smaller. For example, a 10 solar mass black hole would be millions of years, and if you go to 200, it'll be even smaller. So you'll have so that will leave behind. Now, whether those black holes will merge, they would have to form in a star cluster and merge, and then accrete material as well. I mean, accretion could also be an important process. Okay, so the formation of, there's also ideas of primordial black hole forming from the initial fluctuations of the universe. Okay, so these are some of the ways in which you could probably form black holes very early in the universe. Okay.
Okay, sir. Thank you.
Okay, Hamza asks, can the accretion disk be so hot that it starts converting the matter present in it into plasma or any other state? No, the thing is that the accretion disk is very hot. Okay, for example, if you take the sun, because if you just do gravitationally hydrostatic equilibrium of the star, right from using Chandrasekhar's equations of just stellar structure, that which are beautifully given in his book, that automatically leads to a high temperature in the center. So similarly, an accretion disk, particularly towards the center, would be extremely hot, and that is why you begin to see emission from objects at accretion disks in the X-ray or the ultraviolet region of the spectrum. There's a very wide range of emission which is given by this, the vicinity of the black hole, right from radio waves to gamma rays. But for example, there's something called a big blue bump. Okay, in case of a big blue bump, while modeling the spectral energy distribution from the center of an active galaxy or from a solar system, that you'll find that the emission from the accretion disk or inner parts of the accretion disk is at high energies, X-rays or ultraviolet region of the spectrum, and the material is in a plasma state. It is ionized. As you go further and further away from the central region, it'll get cooler. Okay, but right in the central region, it is in the plasma state. And you can also have a disk which is much further away, which may be more neutral as well and contains atomic gas. Okay. So Stavia is asking, in case of further questions, how may you contact you? Actually, my email is there with Rituraj, and I think you can, if he shares that with you, you're welcome to email me anytime, and I will try to answer. But it may take me a day or two to answer, but I'll definitely respond to your questions. Okay. Okay. Thank you. Thank you very much. Thank you, Suman.
Thanks, thank you very much, Sykes. It's
You're
really
welcome.
great talk.
Yeah, I probably tried to cover too much. I just was wondering whether, I hope they all got something out of it. Yeah. Okay.
Yeah, also listening to this talk in different perspective.
Okay. Anyway, thanks very much to all of you for being there on a Sunday afternoon. Okay.
Thank you.
Okay, somebody asked for the PPT. I can convert it into a PDF file, which will be smaller, and then send it to you all. Send it to Rituraj and Jamir, and you all can
Yes,
share
sir.
it.
Sure.
I can
Yeah, we
circulate
will
it
check
with
it.
all the participants along with your email ID in case they have any queries, if that's fine with you.
The email ID is also there in the thing, so you all can share that. That's not a problem. Yeah.
Yes, sir. I'll circulate it among everyone. And
Okay.
thank you so much for giving the first talk for Isaac and spending your time to come here for the event, even from Germany.
Yeah.
We were really glad to host this session, and we hope to stay in contact with you for any further events.
Yeah, sure. Thanks very much. I
Yes,
hope it was at the right level because I wasn't too sure where to pitch it, and I hope at least most of you got something out of it. Anyway, thanks for the very generous comments. Okay, so all the very best. Enjoy the rest of the Sunday, and thank you very much again. Yeah.
Yeah, thanks.
Okay, all the very best. Yeah.
Rudraj, can we conclude the meet?
yes, we can conclude.
Sure.
Pranay?
Pranjal?
Yes, sir.